Engineering from Dr. NGP Institute of Technology. Dr. Karthikeyan is an internationally recognized researcher, consistently ranked among the world top 2% scientists by Stanford University from 2020 to 2024. With a major contribution towards sustainability, clean energy, and United Nations Sustainable Development Goals 3 and 7. He is an recipient of the prestigious Taiwan Employment Gold Card Visa for Exceptional Research Challenge and has served as a research fellow under the National Sangchong University, supported by the Ministry of Education, Taiwan. His academic journey reflects remarkable achievements. Postdoctoral fellow at the School of Energy and Power Engineering at Jiangsu University, China, followed by a PhD in Mechanical Engineering from Anna University. He earned his Master of Engineering in Internal Combustion Engine with first class with distinction and as a gold medalist, and his Bachelor of Engineering in Mechanical Engineering with first class under Anna University. He has also held international academic position as the Associate Research Professor at National Singchong University, Taiwan, and is a member of the Honorary Advisory Committee of Indian Professors in Taiwan. Dr. Karthikeyan's research contribution is truly remarkable, with 80 plus peer-reviewed publications, over 3,061 citations, an H index of 33, and an I-10 index of 64. His work significantly advanced the fields of alternative fuels, energy systems, thermal engineering, and particularly hydrogen technology. ECM and 9.8 in JCP. He has successfully supervised 2 PhD scholars, with one former student currently pursuing a postdoctoral fellowship at IIT Guwahati. His contribution to innovation include 8 granted design patents, 5 registered copyrights, 2 more in progress. He has successfully led several funded projects as PI and co-PI, including DST Seed, MSME funded innovations, Sadhu international collaborations, and AICT supported FDPs and conferences. He also coordinated major initiatives such as the MSME TBI, AICT Vani conference, and Atal FDP. Additionally, he contributes to the global research community as an editor of an Elsewhere book and reviewer for more than 20 reputed international journals. Given his deep expertise in sustainable energy systems, hydrogen-based fuels, infrastructure development, and global research collaborations, Dr. Karthikeyan is ideal expert to illuminate today's topic on hydrogen supply chain and distribution infrastructure. Dear participants, let us warmly welcome Dr. V. Karthikeyan, sir. Sir.
Yes, sir. Thank you very much for your wonderful introduction, sir.
Thanks, sir. Thank you. Please continue, sir.
Shall I start the session, sir?
Yes, sir.
Okay, sir. Okay, I formally once again thank the GRT Institute of Engineering and Technology Management Principal and HOD Sir Edwin Gio and coordinator of this FDP, Dr. Dilipan, for giving me this wonderful opportunity to give my keynote session in this 6 days Atal sponsored FDP program on green hydrogen and advanced storage technology for a sustainable and carbon-free future. And today my session is focused on hydrogen supply chain and distribution infrastructure So myself, Dr. Karthikeyan Vishwanathan, Associate Professor, Department of Mechanical Engineering, Dr. NGP Institute of Technology, Coimbatore. And I think Gio sir has given already a wide information about me. So currently I work over here. Before that, I worked in Taiwan as an Associate Research Professor, and I have completed my postdoc in Jiangsu University, China. Then I am in the top 2% of scientists, and I have published journals in like Chemical Engineering Journal, Applied Energy, Renewable Energy, then Energy Conservation and Management, like all top tier journals in elsewhere. I have published the research articles. Then I have completed 2 research scholars, and one is currently working as a postdoctoral fellow in IIT Gauhati. And funded research projects, I have nearly 80 lakhs plus, and another 2 or 3 is in currently progress and review. So first we will discuss about what is meant by hydrogen, or like what are the methods we can do with the hydrogen. So in general, this figure represents the what are the different types of hydrogen we can classify. So first is green hydrogen, blue hydrogen, and gray hydrogen. These 3 are considered to be the important hydrogens in general. Beyond that, other hydrogen methods are considered like black hydrogen, pink hydrogen, then turquoise hydrogen, and yellow hydrogen. So if you take in the case of this one, the first 3 are majorly used for research as well as in the real-time implementation. This is currently in real time itself, it is in very good condition. That is like TRL is greater than, that is technology readiness level is greater than 8 is currently in this one. So if you take in the case of gray hydrogen, steam reforming process is considered to be the major one, and the source for producing the hydrogen is considered to be a natural gas. Similarly, for blue hydrogen, steam reforming with carbon capture, over here also natural gas as well as water splitting technology, all are considered to be over here. If you take in the case of green hydrogen, electrolysis is considered, and the source for producing hydrogen by means of electrolysis method is dependent on renewable energy. If you take in the case of black hydrogen, it has high carbon content production methodology by means of gasification process. And if we consider carbon capture utilization method, this is one of the prominent one, and the source for this is considered to be coal. Also, this coal can be varied in different processes. If you take in the case of pink hydrogen, it is also by means of electrolysis, by means of either conventional source of energy or by means of nuclear energy. If you do a process and produce an hydrogen, that is comes in the category of pink hydrogen. If you take in the case of turquoise hydrogen, it is by means of pyrolysis process, where if we do pyrolysis process, the temperature will be around 350 to 450 degrees Celsius. We get the ashes, tar, as well as liquid form of material. During this process, we can able to produce the hydrogen, and the source for this is considered to be natural gas. Similarly, if you take in the case of yellow hydrogen, that is also considered to be the process by means of electrolysis, but the process will happen with the help of solar energy, that purely comes in the category of a renewable energy technology. So this gives an outline about my entire presentation, but I am going to focus more on gray, blue, and green hydrogen. So if you take in the case of this one, I have worked with blue, green, and gray hydrogen, where my research articles, that my research works are published in. 2 research works are published in Process Safety and Environmental Protection, and one is published in International Journal of Hydrogen Energy, and another one is currently under review. Then in Journal of Cleaner Production, I have published 1 research article. So with this one, you can able to get an outline about how this blue, green, and gray hydrogen are produced. So my first research work with respect to hydrogen is comparative analysis of hydrogen-rich syngas production from various feedstocks using bubbling bed fluidized gasification process. So if you take in the case of this one, we consider this gasification process. Gasification has a wide variety like updraft, downdraft, then crossdraft, then followed by this bubbling bed. This bubbling bed is considered to be a more effective way of producing the syngas. So if you take in the case of syngas, when we burn the material, we get the combination of gases. The combination of gases is considered to be syngas, that is synthesis gas. If you take in the case of synthesis gas, it has components like hydrogen, carbon dioxide, carbon monoxide, as well as methane. In this, the predominant amount of energy is available with hydrogen, but we want to do the separation process, purification process, filtration process, then only we can able to move for the storage condition. So this work is related with like plastic waste, sewage sludge, and RDF based burning and producing the syngas. So this work gives an outline about how the hydrogen is produced from by means of using gasification process. The next one research work is based on if you take in the case of biodiesel production process, we will consider non-edible source as an input for the transesterification process. When we do the transesterification process, we get the two byproducts. One is biodiesel, another one is glycerol. If you take in the case of biodiesel, that can be taken for direct application in the engines. But if you take in the case of this glycerol is purely considered as a waste material, or it consists of a high amount of fatty content that can be considered for soap manufacturing. But this research work gives an information about that waste can be converted into an hydrogen. So if you take in the case of this one, we consider the glycerol raw material and we do the gas steam reformation over here. We consider the water over in this GSR and we produce the syngas. But the syngas is considered to be a raw syngas which cannot be like a purified form. For the purification process, we are considering that for water gas shift reactor. If we consider this, we can able to separate the hydrogen and carbon dioxide. Then followed by if we consider the PSA, it represents pressure swing absorption method. If we do this process, we can able to extract the purest form of hydrogen, and the remaining is considered to be a combination of urea content source. So we consider the urea separation process and we can able to produce the urea over here. The syngas can be taken for power generation and we can able to create the energy from this method. So if you take in the case of this one, it looks like a glycerol can be converted into different forms, but we over in the research, we consider like different types of scenario based analysis and life cycle assessments and techno-economic analysis to select which scenario is best for the real-time application. So this research work is accepted for publication and it is published already in International Journal of Hydrogen Energy. The next research work is like we consider the hydrogen, but we have considered for only storage process. But if we take it for the engine application, how it will react, we have reviewed that. So if we consider the hydrogen and we have implemented in the compression ignition engine, but we did not consider the conventional fuel like diesel as a working medium. We have considered other types of biodiesels like Jetropa, or if you take in the case of neem oil based or soap nut oil based, like different biodiesel based hydrogen, how it reacts and how the energy from the engine is converted, or what is the maximum amount of energy we can able to extract, is researched in this review work and it is published in International Journal of Hydrogen Energy. The next research work is also a review one where hydrogen production from different feedstocks we have considered. So if you take in the case of feedstock, it varies from different types, like glycerol can be used, or if you take in the case of anaerobic digestion after the process of biogas, we can able to extract. If you consider gasification process, we can able to extract. So we have reviewed this process. The review is based on four major types. One is like blue hydrogen, that is hydrogen produced from water. Then gray hydrogen, that is produced from fossil fuel. Then biomass based hydrogen, that is produced from thermochemical conversion like pyrolysis, then gasification, then purification process. Then different types can be considered for thermochemical. Then like hydrogen produced from biological is considered to be a green hydrogen approach. So this review is published in Process Safety and Environmental Protection. So the last one is like it is directly related with real-time application like Toyota Mirai car. So if you take this research work is like comparative life cycle assessment and economic analysis of methanol hydrogen production process for fuel cell vehicle. This fuel cell vehicle, we have considered the Toyota Mirai fuel cell vehicle. We have considered the working condition of it, and we have considered different scenarios to produce a hydrogen as well as methanol. Based on this, which approach is prominent for an fuel cell vehicle to get maximum amount of hydrogen for its utilization is explored in this research work. So this is published in Journal of Cleaner Production. So these 5 works gives an outline for me to give this presentation, how the hydrogen can be produced, or how it can be implemented for an engine application, or how it can be implemented for a fuel cell application, or how it can be implemented for combined heat and power application. This gives an outline about the entire presentation in a depth way. So first we will discuss about the background of an hydrogen, that is blue, green and gray hydrogen. So for this, the base of why we require hydrogen is the depletion of fossil fuel as a major factor. On another side, increase in fuel cost is considered to be another one important parameter. And other one is the greenhouse gas effect. That means environmental emission plays a vital role, which pollutes the environment and degrades the resources in the nature. So if you take in the case of in general, carbon emission for energy is nearly 73.2%. For producing energy, we want to give carbon emission nearly like 100. That is only a 26 or 27 percentage of energy extraction. We are giving 72 to 73 percentage of energy to the environment. This gives an information that if it increases like our capital of India, how Delhi faces, other states and other districts may also face similar type of condition. So this plays a vital role. If you take in the case of transportation alone, 16.2% is considered to be the emission, carbon emission from the energy production. But if you go for either electric or if you go for hydrogen based operation, we can able to reduce to a certain level. So if you take in the case of why hydrogen is considered to be an important factor for this is that we have shifted from IC engines to electric. From electric, the next version we can expect is the fuel cell vehicles. This fuel cell vehicles operates with hydrogen as a major source. For example, if this one gives a comparative information about the weight and volume of energies. If you take in the case of diesel, the weight of the fuel may be 43 kg and the liters capacity is 46. But if you take in the case of lithium ion and the compressed hydrogen, we just estimate 100 kilowatt hour of electrical energy. If you take 6 kg of hydrogen, we can able to obtain 200 kilowatt hour. But for 100 kilowatt hour, we want required 830 kg of source as well as 670 liters of energy to produce the similar type of work. For this only, compressed hydrogen is considered to be an important factor, but the drawback is that the stability of the hydrogen is not a stable one. Also, the corrosion effect of the hydrogen is higher, but the researchers are progressing towards that to make a stabilized hydrogen and a corrosion-free material to withstand the compressed hydrogen in the container. So this gives an information about that. And if you take in the case of volumetric and graviometric analysis, pure hydrogen and liquid hydrogen are considered to be the more important one when compared to conventional fuels. When you take conventional fuel, volumetric density is higher and graviometric it is lower. But if you take in the case of liquid hydrogen as well as the pure hydrogen, you can able to find it has a low volumetric as well as low graviometric condition, which can be used or it can be transported or it can be taken for the application or it can be stored. Only thing is that the material considered to be an important one in this condition. But in another 5 years, we expect that this energy is considered to be important source. If you take in the case of countries like South Korea, Japan and all, already they have started shifting from electric vehicle to the fuel cell vehicles because they have started developing the hydrogen beds for producing the hydrogen and storing and transportation. So in another 5 years, we can expect other Southeast Asian countries will implement hydrogen as an one of the source of energy, like how we shifted from IC engines to electric. Similarly, other Southeast Asian countries will start migrating from electric to fuel cell vehicles because the fuel cell vehicles are more efficient. Carbon emission is zero as well as it can able to operate for a long period running operation when compared to an electric vehicle. So if you take in the case of hydrogen, it is like used for 30% in refineries, 63% in chemical industries, 6% in metal and glass processing, and 1% in other conditions. So if you take in the case of entire one, the requirement of hydrogen is very higher. The production method is available. The only deficiency occurs with storing and transportation. So if you take in the case of production methods, I wish to give an overview about what are the process available for production, then storage and transportation. If you take in the case of production, hydrogen can be produced by either starch and sugar crops as a source, or water by means of electrolysis, or glycerol by water steam reforming method. As well as I have mentioned earlier, natural gas is considered to be important source for hydrogen production. Similarly, if we go for green hydrogen, biomass is considered to be important source, as well as when we consider the waste material like aluminum or iron ore, after extraction or recycling, we can be able to generate hydrogen, and also we can be able to produce the power from these sources. Then followed by, if you take in the case of storage, we have two different type of storage. One is called compressed hydrogen storage, that is by means of air as a medium, and another one is liquid hydrogen storage. Then if you take in the case of transportation, it can be transferred like pipe transportation, ship transportation, as well as truck transportation. So this image, this one gives a clear information about what are the current as well as upcoming hydrogen production technologies available in the world. So like from T1 to T11, that means so it starts over here and it ends here. This gives the entire information about what are the current methods used to produce hydrogen and what are the technologies. So if you take in the case of first one, glycerol, that is considered to be a technology one. By steam reforming, we can able to produce hydrogen. Similarly, glycerol, steam reforming, we can able to produce hydrogen. If you take technology 3, that is waste biomass, we can do biogas and we can able to produce steam reforming method and hydrogen. If you take in the case of starch and sugar crops, we can do fermentation, then distillation, then ethanol. This ethanol can be steam reformed and we can able to produce hydrogen. If you take in the case of like biomass drying, gasification, already I have told that like upward draft, upward gasification, downdraft gasification, cross draft gasification, or bubbling bed, we can able to do, and we can able to produce the syngas. That syngas can be further purified and we can able to produce a hydrogen. If you take in the case of residual crops, we can do that by pyrolysis, and by chemical looping we can able to produce hydrogen. Similarly, if you take water, by electrolysis we can able to produce. Similarly, if you take residual crop and if you do dark fermentation, we can able to produce hydrogen. Similarly, aluminum, we can able to produce hydrogen. If you take in the case of this one figure, gives a clear information about nearly 11 different technologies are available in the current scenario to produce hydrogen with a maximum possible method. Next, we are going to explore about what are the methods of technologies available to produce hydrogen in an in-depth way. Like first one, we are going to deal with steam methane reforming of natural gas. If we extract the fossil-based natural gas, we can able to do hydrogenation and steam reforming. If you take steam reforming is nothing but natural gas as fuel and admitting steam to the system and producing the syngas. So syngas is the combination of hydrogen, carbon dioxide, monoxide, and methane, and by means of WGS, that is water gas reforming, as well as PSA, pressure swing adsorption method, we can able to produce hydrogen. Then if you take second one, that is gasification process of biomass of hydrogen production, if we consider a biomass, maybe a woody biomass or like a crop based biomass, when we do drying and if we consider the gasification process, we can able to get syngas. This syngas, after cleaning, scrubbing, filtration, we can able to produce a quality syngas. Then followed by means of WGS, that is water gas shift as well as pressure swing adsorption, we can able to produce hydrogen. This off gas represents other gases available in the syngas like CO, CO2, and followed by methane. That and all considered to be the off gas, and by pressure swing adsorption method, we can able to produce 99.9% purest form of hydrogen. Then steam and autothermal is considered to be the technology 3 and technology 4 for hydrogen production by means of biogas. When we do the fermentation process or anaerobic digestion process, we can able to extract the biogas. Sorry. That biogas, when we go for the purification process by means of applying the steam reforming as well as autothermal reforming, we can able to produce the syngas. This syngas further, the by means of water gas shift reaction as well as the PSA, we can able to produce the hydrogen. Then followed by, if you take in the case of alcoholic waste for hydrogen production, if you take in the case of beverages, or if you take in the case of wine manufacturing, we will get more amount of waste from the industry. That waste will consist of more amount of ethanol. This ethanolic waste can be converted into an hydrogen, and the method is like when we go for steam reforming method with a 20% of ethanol with the material what we obtain from the beverage waste, and with by means of catalyst and by means of steam introduction, we can able to produce the syngas at very higher temperature. This syngas further purified and separated by means of WGS and pressure swing adsorption, and we can able to produce hydrogen. Then followed by glycerol steam refining process for hydrogen production is considering the like oil based, like it may be a jetropa, or it may be a rapeseed, or it may be a neem oil, or it may be any type of non-edible oil. By considering transesterification process, we can able to separate biodiesel and glycerol. This biodiesel, by means of washing, we can able to extract and improve its quality, and we can take it for the market directly. But if you take in the case of glycerol, it is considered to be a waste product. This waste product is by means of steam reforming, we can able to improvise its quality, and we can consider by means of steam introduction, we can able to produce the syngas. This syngas is taken for waste gas, water gas shift reaction and pressure swing adsorption, and we can able to produce hydrogen. If you take off gas, we can able to consider that as an another one form for improving the steam reforming process in case of hydrogen production by means of glycerol as a raw material in this technology. This is the seventh technology, that is AG2S, that is a silver sulfide based process. If you take in the case of this one, this process is considered to be an amine wash process, and we can able to get the syngas, and we can able to improve its quality by means of WGS and PSA. So if you take in the case of entire 7 technology, we can able to find two process or uh, two conditions is important to separate, purify, and take the hydrogen from the combination of different gases like in a syngas. So in that, two major part is WGS and PSA. Next, we are going to discussing about what is WGS, how it looks like, and how it process, as well as how this PSA looks like and how we do the process. So first, we will see about WGS, that is water gas shift reactor. So this water gas shift reactor is nothing but a reactor which consists of a catalyst which can able to operate with a pressure of 1 to 6 megapascal and a temperature of 180 to 250 degrees Celsius, and it can able to produce, or it can able to extract or separate hydrogen from this. So it is like it has some amount of other gases too. By means of PSA, we can able to improvise. So the input for this is CO and H2. After the steam reforming process, we will get carbon monoxide and water or steam as the input for this WGS, that is water gas shift reactor. By means of this catalyst, pressure and temperature, we can able to make the gases to separate each other. So for an example, I have shown our graph over here. The x-axis represents the temperature and the y-axis represents the flow rate. So if you take in the case of this one, when we increase the temperature beyond 250 degrees Celsius, this is a theoretical analysis. When we go beyond 250 degrees Celsius, you can able to observe a peak improvement in the hydrogen in all the cases as well as all the scenarios based on either temperature or based on pressure as well as water flow rate. If you take increase in hydrogen, which reflects a decrease in CO2 and CO. So this condition represents that when we do the process at higher temperature with the water gas shift reactor, we can able to produce a purest form of hydrogen with high mass, that is a high amount we can extract from this WGS reactor. So I hope you can able to get the outline about what is this WGS. Now next we are going to see about the PSA, that is pressure swing adsorption method. Pressure swing adsorption method is nothing but it has two beds. One has an zeolite and another one has an active carbon as a material. So if you take in the case of this one, it has a different valve arrangement where it does nearly six process that is represented over here. We give the input as an hydrogen and carbon dioxide. When it does the conversion process, at last we can able to extract the hydrogen and we can able to extract the purest form of CO2. So this process is called as a pressure swing adsorption method. This is a large scale application method where if you take in the case of gasification process, after the syngas is produced, after the water shift reaction, this is considered to be an important one to produce the hydrogen with more amount of like purity of 99, greater than 99 percentage, we can able to extract by means of this pressure swing adsorption method. Other types, that means still this one represents based on high amount of energy requirement, large scale implication, then large amount of money investment, all this comes under till technology 7. If you take from this method, it is like a compact methodology to produce the hydrogen, maybe a compact one with a high amount of accuracy we can able to extract. In this, the first technology in general, each one can able to understand is the water electrolysis process. That is splitting of a water into hydrogen and oxygen. In lab scale, we can able to do that. But when we go for real-time implementation, we want to do the separation process. Like when we consider an electrolysis, we will consider water and KOH. Then followed by if we apply the electricity, if you take in the case of stack of materials and application of water based on the anode cathode reaction, we can able to extract. This is lab scale application. When we go for large scale application, the purest form of hydrogen production depends on the gas liquid separation and gas gas separation. So in gas liquid separation, it represents that separates the KOH and it takes the gas to the next level. Then in gas-gas separation, where it has some amount of oxygen that is removed and the purest form of hydrogen is taken by means of this process. This is called a water electrolysis process. Then followed by oxidation of aluminum. This is in case of real-time industrial application where aluminum is considered to be an raw material over here. With this aluminum, when we go for oxidation process, that is a combustion, then followed by it can able to produce an high amount of energy based steam that is allowed to the steam turbine where we can able to extract the energy. Then the low pressure heat is taken for the hydrogen production. This is considered to be the oxidation based aluminum to produce the hydrogen. Then followed by, if we take in the case of this dark fermentation method, it is also currently available in large scale application. Like if we take in the case of materials like rice husk or wheat husk, after removing the source from that, the outer layer is considered to be a waste. That waste is considered and it is taken for milling, then hydrolysis process, then filtration. From filtration, we go for sarification process and dark fermentation. In dark fermentation process, we consider wastewater from the beverages industries, which has some amount of ethanol as well as some amount of alcoholic material, which enhances the process of dark fermentation. By means of this, we can able to extract purest form of hydrogen as well as it has some amount of volatile fatty acid as well as CO2. But this is real-time application process where it is purely dependent on the biological principle. So this dark fermentation is considered to be the biological process to produce an hydrogen method. The last one is ion-based chemical looping. What we have discussed earlier in the case of aluminum, similar approaches over here, and we can able to extract the hydrogen from this method. So I hope you can able to get an outline about the 11 technologies which is currently available in the market as well as in the research field to produce hydrogen either experimentally or if you take in the case of process modeling method or by considering the carbon credit or by considering the techno-economic point or by considering the life cycle assessment or simulation. All this can be possible with this 11 technologies, and these 11 technologies are considered to be the prominent one for producing the hydrogen in real-time condition. So if you after producing that hydrogen, storage and transportation plays a vital role. So in general, storage is classified into two categories. One is physical storage, another one is chemical storage. If you take physical storage, it is by means of compression, liquefaction, and followed by cooling method. So if you take in the case of compression, we can able to compress the gas and we can pass the gas by means of pipeline for transportation. Also, we can able to load the gas in a gas container and we can transport by means of trucks. Similarly, liquefaction is like a liquid-based hydrogen which can be transported by any method. Then if you take in the case of cooling, it is considered to be a cryogenic based hydrogen. This cryogenic based hydrogen also can be transported. But if you take in the case of chemical storage, it is based on the absorption of the condition only we can able to do the storage process. That may be a physical or it may be a chemical. If you take physical, it is based on two methods. One is metal organic. This field is considered to be one of the prominent one in many countries to perform the research. Another one is carbon nanotubes. If you take chemical absorption, it is by means of metal hydrate, then liquid organic. So all this can be transported by means of trucks. So if you take in the case of this one, it is classified into physical and chemical storage. But when we do the process, chemical storage research is still a booming one where different types of approaches are currently investigated to make the hydrogen to be stable in chemical method and for transportation. But if you take in the case of physical method, if you take in the case of physical method, the gaseous mixture or a liquid mixture or a cryogenic mixture can be transported and it is currently in practice in some of the countries. But chemical method is currently in different levels and it is taken for the application for transportation as well as storage. So for once again, we just go on an overview about an hydrogen, that is a green hydrogen. So if you take in the case of green hydrogen production, these are considered to be like if the previous 11 technologies, what we have discussed gives an information available one, it may be a biological or it may be a gray or it may be a green or it may be a blue or it may be a pink or it may be an black, like hydrogens, all methods we have discussed. But particularly over here, we are going to start an overview about what is meant by green hydrogen. So this green hydrogen represents that the environmental impact of this green hydrogen is very low. The carbon emission from this method is very low, as well as this method can be taken up research as well as for real-time application is also more feasible. So if this may be like a small compact of green hydrogen method is also possible. Some of the methods are listed over here like electrolysis of water, photocatalysis, then photoelectrochemicalysis, then followed by biophotolysis, dark fermentation, photofermentation, and thermal chemical splitting, that is water splitting method. So over here, if you take in the case of this one, it represents a biological based green hydrogen production method where it is clean, sustainable, and it does not have any impact on the environment. So we have discussed green energy is there, but what about the country-based point? So if you take in the case of country-based point, green hydrogen are highly researched in China, Australia, Germany, United States, and Saudi Arabia. In major, China has the high amount of production capacities for this hydrogen production method. They have a lot of algae-based approach, biogas-based approach, then beverage-based approach. It has a large one. Other countries are also focusing on this method to produce a prominent, then optimized hydrogen based on the green approach. So if you take in the case of this one, green hydrogen capacity, that is, if you consider one technology, that is electrolysis, it requires the energy from an external source to operate that fuel cell or operate that electrolyzer. So for this electrolysis, we need an energy input. The energy input can be obtained from renewable as well as non-renewable. If you take in the case of this one, this represents a green hydrogen. Therefore, we may not dependent on the fossil-based energy production approach. We will go with the green energy approach. So green energy approach represents a renewable base like solar, wind, hydro are considered to be the important one. So if you take in the case of this one, from 2020 to 2023, I have shown this graph where solar powered electrolyzers are increasing, wind powered electrolyzers are also increasing, but if you take hydro powered electrolyzer are still in stagnant condition because hydro based approach may not be an prominent one to produce the energy to power an electrolyzer. But if you take in the case of solar, it is a pure clean energy available all around the year. If you take in the case of wind energy, based on the pattern of wind, we can able to extract to a maximum of 8 to 10 months in a year. Therefore, you can able to find that green energy with an input from the green energy is considered to be an important one in the renewable energy sector. So this gives that how this renewable energy market. So this renewable energy market is considered to be an important one where it helps for decarbonization, then carbon credit, then energy storage, export market. It has a different advantages when considered with an non-renewable source of energies. So if you take the potential of it, it has potential in three categories. One is power, industrial decarbonization, and transportation. If you take in the case of previous, we have discussed that the electrolyzer which has powered with solar, a electrolyzer powered with hydro, or a electrolyzer powered with wind, which represents it is a pure clean energy. This energy can be integrated with the grid, like what we are using for AC/DC grid, we can able to integrate. So it helps to reduces the carbon emission. Also, if you take in the case of industrial decarbonization, when we produce an hydrogen by means of a natural method, we can able to decline the emission when compared to an like industrial based approach. Similarly, transportation, we are using IC engines where it produces large amount of emission to the environment. When we consider electric vehicle, it also produces some amount of energy with a different factor. But if you take fuel cell technology, it does not produce an emission to the environment, but it helps to increase the carbon credit to the environment, which helps to maintain the atmospheric stability for a long period of time to achieve the environmental sustainability as per the United Nations Sustainability Development Goal. So some of the barriers over here is technology, economic, and policy. If you take economic, scaling is considered to be important one. Like it may be like a 4 kilowatt production method. We cannot be able to extend for 400 kilowatt. That is considered to be a scaling technological barrier. Similarly, the production cost and market competency. But if you take in the case of economic, we need to have more regulations and scaling of procedures. Also, if you take policy, regulatory and insufficient incentives are available for this method. But this considered to be an important one as per the sustainability development goals. So if you take in the case of carbon credit achieved by green hydrogen, these are the different years of information on carbon emission reduction by means of green hydrogen application, where you can able to find, if you take in the case of India, in 2020, it is around 0.5. But if take in the 2023, it is around 1.8. The government of India has taken different initiatives to produce green hydrogen. One such is recently, like 2 or 3 years before. That means if you take 2022, we can be able to obtain a carbon emission reduction by 1.3. Similarly, on the same year, Nitin Gadkari, our minister, has introduced the Toyota Mirai, that is car as a hydrogen powered vehicle, that is fuel cell technology vehicle in India, as a test drive, and is currently in the road testing and are waiting for the RI approval. If it is approved by the RI, surely within another couple or 3 or 4 years, we can be able to find the same vehicle what we are seeing in the photo will be in the real time in our roads. So when this cars comes to the market, the dependency on the electric vehicle, what we are doing now may reduce, and the people will shift from electric vehicle to fuel cell technology. That means hydrogen powered vehicles. Sorry. So these are some of the photographic images of hydrogen powered vehicles, that is Toyota Mirai. I want to mention that this is not only in India, it is already in Japan, Korea, Taiwan, and some of the Southeast Asian countries like Thailand. They are having this vehicle in real-time application. So similarly, they have taken that vehicle for India real-time investigation. When it is approved, surely this vehicle come for the market from Toyota as a fuel cell electric vehicle technology. So if you take in the case of fuel cell electric technology, this is the cross section of it. Also in the first slide, that is during my research work, I have mentioned the life cycle assessment base. Over there, we have considered the same Toyota Mirai vehicle as our case for producing, that means produced hydrogen to be considered to be the source for the vehicle to operate. So this is the cross section of this, which represents that fuel cell is not a least one when compared to an electric vehicle or a that is battery-based technology. Surely within another, that means we can expect within 2030 or 2040, we can find these vehicles to be in our roads. So this is the policy framework and policy this one. So we can go for a supply chain model now. So I have touched upon the what are the production methods for hydrogen. Then I have touched upon what is meant by green hydrogen. Then I touched upon what is meant by this fuel cell vehicle and what is this Toyota Mirai. Now we are going to the hydrogen supply chain models. So when we consider a model like this one, so this is based on the scenario based analysis. So supply chain is like when we consider a raw material, we cannot depend on the same raw material to produce the energy. We want to be like consider different raw materials to produce that energy. So if you take in the case of this one, this gives an outline that we have considered hydrogen production by means of water electrolysis, then steam methane reforming and gasification process. The end products are two. One is hydrogen as a gas and hydrogen as a liquid. If we consider hydrogen as a gas, how it is purified and how it is taken for the industry. If we consider as a liquid, how it is taken or stored, then how it is taken for the application for the real time. So this is a simple framework of a supply chain of an hydrogen from production, purification, storage, as well as the end user. So this is another one diagram which represents more over same, but we can able to get more information like we first depended on the energy source, what type of energy sources we are considering, then what are the feedstocks we are going to consider, then what is the physical based process and what are the material based process. Physical based process means either it may be a compressed one or cryogenic or liquid one, or what is the method we are going to implement. Then material based is like how we are going to store it by means of like a physical storage or chemical storage, either like a metal hydrate method. What is that? Then how we are going to transport and how it is going to reach the end user. So this is a diagram which represents the supply chain of it. So this one gives an outline about agents in supply chain, that is hydrogen supply chain. If you take in the case of this one, it is dependent on two major H. The one H is hydrogen institutional agent. Another H is hydrogen infrastructure agent. These two agents for any analysis we want to consider. If you take institutional agent, it is based on government, regulatory body, industry, supplier, society, academia, research, then intermediators and banks and investors. So this hydrogen institutional is important. Then only we can able to come to a conclusion which hydrogen approach we can able to go. If you take in the case of hydrogen infrastructure agent, it is like how we are going to produce our hydrogen. Either we are going to dependent on solar PV, or we are going to dependent on the wind energy or nuclear or methane or SMR or carbon capture system or road transport or storage. So these two H combines only the end user will get benefited. So when you consider hydrogen institution and hydrogen infrastructure in a supply chain, when these two matches only, we can able to benefit our end user. So this is also one of the optimization approach, but over here, I am going to take the case study of one supply chain model in South Korea. So we have a collaborative research with South Korea, that is the Seoul Tech University in Korea. So we have a very good collaboration and we have formulated a research based on that. So for that research is like a hydrogen supply chain model. So this work gives an outline about how we are going to consider or based on cost or based on technology or based on the production rate, how we are going to optimize a process and how we are going to take it for the real-time implementation. If you take in the case of Korea is already having a hydrogen bed for hydrogen production and application for its vehicle as well as for the industries. So over here, we have considered green hydrogen, then natural gas-based hydrogen, then waste refinery-based hydrogen, and hydrogen from the ammonia, that is by based on NH3. In all these production methods, we have considered different transmission process. Like we have considered tube trailers, then LH2 trucks, then pipeline-based process, then tanker trucks. So we have considered this as the transmission process. Then we are considering the terminals. The terminals is the storage unit like a gas storage, then liquid hydrogen storage and liquid storage. Then we have considered the distribution. For distribution, we have considered tube trailer distribution, then liquid hydrogen trucks, pipelines, and tank trackers. Then followed by, we have considered the hydrogen refueling stations. The stations is classified into three categories. One is gas type, then liquid hydrogen type, and liquid hydrogen compressed type. So this is a model we have considered for hydrogen supply chain in a Korea, that is in South Korea. So when we go for this type of analysis, we have mentioned that we have different transmission methods. For less than 100 kilometers, we have considered truck-based. If it is greater than 100 kilometer or nearly like greater than 1,000 kilometers, we have considered the pipelines. If it is like greater than 1,100 kilometers, other approach, like different cases we have considered and different scenarios we have considered. For this model, we have considered zones and regions. Like we have considered different province. In our country, we are considering that as a state. In other countries, we have considered that as a province. So we have considered each province as a zone, and the zone is classified into regions. That is like a northern region, southern region, eastern region, western region. So for this one, how we can able to consider a station and how we are taking our fuel from one position to another position, like different cases we have considered. Like we have taken zone Z and zone Z dash. We have departing inventory and followed by arriving inventory. So if you take in the case of this one, it has two major conditions. One is called charging, discharging, and traveling. So one is from the produced station, we want to charge a tanker. Then the tanker wants to travel and it want to depart. Then once again, the departed one want to come for the charging station to once again charge and taken for the arrival. Like different conditions based on the optimization method, LSTM and particle swarm optimization, as well as random forest. All this we have considered for the optimized scheduling model. Then this one represents like we have different provinces we have considered. In the province, we have considered like one station for producing the hydrogen, which may be possible by 2050. But currently, it has a platform. But that platform has to be extended in all the provinces, where the provinces by 2050 can able to achieve this much amount of hydrogen production technology. Like what we are having in our country, like an Indian Oil, Bharat Petroleum, then Shell, like all the fuel stations, what doing is that it collects the fossil fuel from one side and transported, and it is taken for the distribution station. Similarly, sorry, over here also we have considered hydrogen is produced, then it is stored, then it is transported, then transported to the distribution center. So like this, we have studied this in 2023 and we have projected till 2025, where we can able to find like vehicles like Toyota Mirai and other like Hyundai vehicles all comes for real time with a large amount of acceptance from the customer, where we can able to find a higher increase in the requirement of hydrogen in the upcoming years is possible. Like what we are facing currently with the electric vehicle technology, the similar one we can accept by another 5 or 10 years with the hydrogen approach. So this is an liberalized cost hydrogen approach, where you can able to find that we have analyzed for 6 years. That means six consecutive years we have considered. The first year you can able to find the investment of pipeline is higher. But when the year prolongs, we can able to find the investment cost is zero, which represents that with the developed pipeline, we can able to move our liquid or gaseous medium of hydrogen from production station to the distribution station. Similarly, if you take the production investment is also more over a constant term for the entire period. And after, if we have considered only 6 years of operation, if we have considered for 25 years of operation, the investment for the production method may have further declined. Similarly, if you take in the case of transportation cost, it increases, which represents that the demand is higher, the production needs to be increased, then the transportation need to be increased. So it is like a moreover vice versa mechanism for the 6-year analysis. This is the overall expansion planning cost by the sector of hydrogen, where you can able to find the pipeline investment as well as the production of hydrogen investment is more over higher in the supply chain sector. So when we consider the pipeline investment and the production investment after a period of 10 years or 15 years, this cost may get reduced, but the initial investment is higher. That is only represented in this figure based on the analysis. Then installed capacity for the production like the CB, CN, GB, then GG, all the x-axis represents the each province and the y-axis represents the production capacity. So if you take in the case of this one, initially green hydrogen, domestic hydrogen, the hydrogen by refinery and imported hydrogen as an ammonia. So all this you can able to find different provinces based on the population, it varies. If you take in the case of population of GG is more higher when compared to other provinces. So if you take in the case of truck requirement for the moving of hydrogen from one location to the another location, when we take for 6 years, we can able to find it starts increasing. This represents that when the vehicle count is higher and the application of the vehicle is higher, we require more amount of trucks for production. That means movement from one hydrogen to another hydrogen station. So this represents that hydrogen is to be the future, but it takes some time for the real-time implementation. So this one is installed at capacity for storage for period and followed by period of the cities. Like over here, you can able to find that what are the cities like GG representing insulin, then Seoul, then Ulsan, then Juju. So these are the provinces over there. How this medium is required for a long period of time. Like if you take in the case of fossil-based resource, it is identified in the 17th, 18th century, but still in 20th century, we are implementing the same energy for production of like a production of energy by means of a fossil-based resource. Similarly, if hydrogen is evolved surely in another 5 or 10 years, the next rest of the years, like electric vehicle, it is going to be the prominent one for the transportation. Similarly, over here, when the sensitivity analysis is considered, when we increase the demand for a high period, we can able to find the liberalized cost of hydrogen starts decreasing. When the demand is higher, there will be a decrease in the hydrogen cost is possible by this technology. So my first concluding remarks is that many countries started migrating from electric vehicle technology to fuel cell technology, which represents that nearly 80 stations are already available in Japan. It has moved nearly to 150 by this year. So which represents hydrogen implementation and usability started increasing in Southeast Asia. Similarly, if you take in the case of European countries, they also start shifting from zero polluting vehicles to clean energy producing vehicles, that is the fuel cell electric vehicles. So this one represents the clear one, as well as this is the application of our hydrogen, like it can be taken from power to X, carbon capture utilization, then hydrogen application, green hydrogen production method. These are the upcoming or some of the research or some of the real-time implementation is possible. And the key facts and objectives is shown over here. So green hydrogen is considered to be an important one for the upcoming years. The future of hydrogen is shown over here. So if you take in the case of future of hydrogens, currently we are more over here in this two sector, that is on the gasoline based as well as in the case of battery based. But if you take in the case of hydrogen, that is the future, like that is not only for like a passenger car or for an small bike or scooter. It can be used for buses, trucks, as well as it can be used for full-sized truck, or like it may be a long journey vehicle. We can able to implement this technology for a long period of time where the pollution is zero, the production rate is good. Only thing is that implementation is started within another few years. We can able to accept that fuel cell vehicles will rule these roads. So not only we are speaking that fuel cell vehicles started from like after 2010 or 2020. It started in early 19th itself, like end of 19th. In 1998 itself, hydrogen started the fuel cell electric, that is fuel cell based vehicle. So it is currently over here in 2024 of HTWOG grade. That is based on the green energy, how the fuel cell is going to power or how it is taken for a long capacity vehicle. If you take in the case of Korea and Japan, the two major companies like Hyundai and Toyota are mostly focusing on hydrogen based vehicles because it is more efficient than an electric vehicle and zero pollution when compared to an IC engine. So with this, I conclude my presentation and I hope I have given some outline about what is meant by hydrogen supply chain distribution, then how it is produced, then how it can be taken for the real-time implementation. Like all this, I have touched upon. So with this, I have concluded this session. If you have any queries, you can raise your questions now.
Dear participants, if you have any queries, please proceed.
Hello, sir. This is Dr. Suresh from Punjab University College, Chandigarh.
Yes, sir.
Sir, your session, first of all, would like to thank you. It was very informative and techniques available for the production you have explained very well. Would
Thank
like,
you.
not exactly question, would like to request you to provide PPT if possible.
Yeah, sure, sir. I will share it. You can get it from the host. You can get it. I will give it to the host and you can get it from him.
Okay, okay. Thank you.
Sir, Dr. Karthikeyan, sir.
Yes,
Some
sir.
of participants posted questions in chat box.
1 second, sir. I will check it out. Still application. Yes, sir. Like one of my colleague when I work in Taiwan, he was appreciated by the Taiwan Ministry of Environment for his research work. He researched in metal hydrates, where has been called for Japan as well as for the Korea to give his presentation on metal hydrate. He is none other than an Indian scholar who did his PhD in National Taiwan University. It is one of the QS ranking university, and we hope that metal hydrate based hydrogen storage method is going to rule the production, that is storage method, in upcoming years. Because his research work is like well appreciated in many of the professors in India, including in IITs as well as in IISc. He has been called for a presentation in IISc. Now, currently, he is working for Saudi Mobility Center. That is, they are working for hydrogen mobility in Saudi Arabia. He completed his PhD and currently working over there. So, like that, I hope that metal hydrate based storage method is considered to be an upcoming technology. Thank you very much, sir. Any other queries?
Another participant questions are there, sir. Dr. Triju Tharail. Can I read, sir?
Yes, sir.
What are the basic experimental facilities required to start research in green hydrogen production? Can you suggest a few research gaps in green hydrogen production?
Sure, sir. Like in general, when we go for lab-based study, if you take in Tamil Nadu like VIT, then SRM as well as Sastra University, then IITs, then followed by PSG Institute of Science and Technology, they are having the fuel cell testing centers as well as they have the electrolyzer fabrication unit. So based on different materials, how the stack-based electrolyzers are developed, then fuel stack, number of stack-based as well as material of that stack is currently going on research, where we can able to find that electrolyzer, what we are doing in our lab scale is like we are just taking the glass or some other polymer based material, and we are creating the anode and cathode, and we are applying some amount of electricity to that by means of in some amount of volt, and we are doing the splitting of water by means of hydrogen and oxygen, and we are taking that hydrogen directly for bubbling, then scrubbing, then filtering, then we are taken for the direct application. Like this phase we are working on, but we can do more research on the electrolyzer cell packing, like what we are doing with electric batteries, like anode, cathode. In between that, we have a material that electrolyte based on the charging, recharging. Similarly, stacking of material we can consider for a large scale application, sir. Any other queries?
Thank you, sir. Another one, Mr. Immanuel Yobu. What are the economic challenges in building a hydrogen refueling station network?
Hydrogen?
Hydrogen refueling station network.
Sir, like still in India, we have not find any hydrogen-based distribution centers. But if you take in the case of Southeast Asian country, especially in Japan, Korea, and Taiwan, there are few distribution centers are there. Like how we are now currently in a distribution center like a fossil-based fuel, petrol, diesel, we have CNG and LPG as well as electric charging station. In Southeast Asian countries, we have the separate distribution center for hydrogen. Like they use the truck, fill it, then they will distribute it, and from the distribution we can able to take power for our vehicles. Similar type is available, but in India we have started testing about how hydrogen fuel cells can work in our atmospheric condition, in our road condition, then how the driving characteristics over in India entirely different when compared to Southeast Asian countries or Western countries or Middle East. So they have started, and it is in nearly 3 years or passed away, and we hope that ARAI will give the approval for hydrogen fuel cell vehicles in another couple of years. Because if you take in the case of VinFast, a new vehicle of electric based technology in Thailand, they are producing, VinFast is producing fuel cell vehicles, but they have not taken it for India. They have put the plant in Thoothukudi and they have given the electric based vehicle in India. Soon, if Toyota Mirai got the approval from ARI, surely in couple of years, VinFast as well as some other companies like Mahindra, as well as if you take in the case of Hyundai, everyone will start their production as well as their car selling based on the fuel cell technology very soon. Maybe before 2030 or within 2030, we can expect the similar type of trend if ARAI approves. Okay, sir.
Thank you. Thank you, sir. Thank you for clearing queries. And session is very beautiful and very informative. Thank you, sir. Sir, HOD, sir, can I close?
Yeah, sir. Karthikeyan, sir.
Yes, sir.
Very good presentation, sir.
Thank you very much, sir. Thank you, sir.
Thank you so much, sir.
Once again, thank you, Dr. Karthikeyan Viswanathan, for the exponentially clear and comprehensive presentation. We have not only outlined the technical blueprint for hydrogen distribution, but have also illuminated the practical pathways that will turn ambition into the reality. Your insights on the infrastructure challenges are preciously what we needed to ground our discussion in actionable and understanding. Thank you for sharing your valuable expertise and for contributing significantly to the success of FDP on green hydrogen for a carbon-free future. Yeah, heartful thank you, sir. Thank you so much, sir.
Yes, sir. So once again, I wish to express my sincere thanks for the GRT Institute of Engineering and Technology, Tirthani, for giving me this wonderful opportunity. I wish to express my sincere thanks to the principal of the institution, then HOD sir, Edwin Paul sir, and the organizer of this event, Dr. Dilipan, for giving me this keynote session in this wonderful Atal FDP. And thank you very much. If you have any queries or doubts related to hydrogen or radio-based technology, if you need any help or support, you can contact me in this mail ID as well as with the mobile number. I express my sincere thanks for, once again to everyone. Thank you very much, participant, for accepting my lecture in this FTP. Thank you very much, and have a nice
Thank you,
day.
sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Dear participants, next section will start soon. Stay tuned.
Sir,
Yeah, yes.
hello. Sir, I want to speak to coordinator.
Hello. Tell me, sir, what do you want?
So, sir, this is Dr. Suresh from Punjab College, Chandigarh.
Yes, sir.
Sir, I'd like to request you, can you create any link or Google Drive link where we can download the PPTs of the lectures and we can prepare for the examination because certificate is based on qualification only. So
Yes,
we
sir. We
have
will
taken
share
approval
the
and
PPT
the
in the
things.
group, sir.
Okay,
We'll
sir.
share.
Which
Always,
group, sir?
always welcome, sir.
In which group you have shared, sir? WhatsApp group?
Yeah, yes, WhatsApp group.
Have you shared or will be sharing?
Will be shared, sir.
Will be sure, will be sure. Thank
Okay,
you.
if one day advance, it will be better. We can go through it. Last day the examination, I think, becomes tough. We may not get certificate. That is the issue. Would like to request to sharing.
Okay.
Thank you,
Okay.
sir.
Okay. Thank you, sir. Thank you.
Sir, Dr. Yashar Aranfar, sir. Hmm. Sir, kindly unmute, sir.
Hello,
Yeah.
good evening.
Good evening, sir. I am Dr. S. Dilipan, Program Coordinator, Associate Professor from
Okay,
GIT Institute of Engineering and Technology.
nice to meet you. Nice to meet
Good
you,
evening, sir.
Professor.
Welcome, sir.
My pleasure. Thank you, thank you. It's my pleasure. My voice, and everything is okay. Can you hear me clearly?
Sir, pardon?
Can you hear me clearly
Yeah.
or
Yes,
not?
yes, sir.
Okay, okay. And you know, behind my head there is a light. Is it okay for you? If it is not okay, I can
Yeah, no
Blu-ray my
problem.
behind. Okay,
Clear,
Yeah,
sir.
no problem, sir.
No issue.
okay, okay. Okay, I'm in your service.
Sir, shall we start the session?
Sorry?
Shall we start the session?
Yes, I'm ready. I'm ready to start.
Okay, sir. Now I request Mr. Mohan Raj, Program Coordinator, Co-Coordinator, Assistant Professor, Department of Mechanical Engineering in GRT Institute of Engineering Technology, to deliver welcome address.
So good evening, sir. Good evening to
Good
one and all.
evening.
I welcome you all for the session 8 of our FDP program in the topic of hydrogen for industrial decarbonization, steel, ammonia, and refining. To guide us through this complex and vital topic, we are privileged to have with us an expert whose academic journey and research are truly international in scope and profound in impact. Our today's speaker, Dr. Yasser Arifan sir, is an associate researcher at National Cheng Kung University in Taiwan, a position that sits at the apex of the remarkable academic path. He is a rare scholar who holds 2 doctoral degrees, one in advanced engineering science from the Autonomous University of Zores in Mexico, and another in engineering mechanics from Huai University in China. This foundation is built upon his earlier studies in the mechanical engineering at Urmia University. His research expertise is both deep and wide, with a strong focus of environmental science, renewable energy, and geothermal energy system, integrated wastewater treatment, and energy systems. Further, this unique combination of multinational academic excellence, rigorous analytical research methods, and practical engineering experience perfectly equipped him to address today's topics. He will help us understand the potential and challenges and the pathway of hydrogen to transform our most energy-intensive industrial sectors. It is my great honor to invite to the session. Sir, very warm welcome, sir. Very warm welcome, sir.
Thank you. My pleasure. It's my pleasure, and thank you for the introduction. It's my pleasure that today I have this opportunity to make my presentation. I hope that we have a pleasant and useful presentation today. Okay, I'm ready to start.
Okay, kindly take your session, sir.
Okay. Just I need to upload my presentation.
Okay,
this
sir.
is not my. Okay.
Okay, sir. You can upload, sir.
Okay, everything is clear right now?
Yes, sir, clear.
Okay. Okay. My name is Yashar Aryanfar, and currently I'm a research associate in National Cheng Kung University. Today, I have this opportunity to present the topic of hydrogen for industrial decarbonization, steel, ammonia, and refining. It's my pleasure to value this opportunity. Special thanks for all the professors, all the the person in charge that invited me and gave me this opportunity to talk with you. Okay, I want to start my presentation. Now we are in 2025, and why we need to talk about hydrogen. Hydrogen, the reason that today we are talking about hydrogen, why? This is, let's firstly answer this question. Hydrogen today, nowadays in the world, enables sustainable primary energy in all sectors of the economy. Including the industrial sector, transportation sector, the houses, all the sectors that we are including in our economy. And the hydrogen has this potential to cover all these demands. Because of that, it's one of the most important candidates for the future fuel, that we are talking these days. Secondly, hydrogen has sufficient energy density for end uses, including heavy duty transport. Heavy duty transport means that, the cargo, airplanes, the ships, the big containers, and every big vehicle that in the transportation, we are considering them. Secondly, hydrogen is a building block for zero emissions fertilizer and chemicals. In the chemicals, sectors, in the most sections, especially in steel, especially in ammonia, all sectors, hydrogen playing a critical roles, and this role gives opportunity to hydrogen to absorb enough attention all over the world, for the researcher, for the government, for the politicians, and the rest of the person in charge. Hydrogen is sufficient to enable a 100 zero emission grid. Why? Why? Because it's so easily when the hydrogen is burning, instead of CO2, we have water, H2O, and it's simply, decarbonize in the very simple word, decarbonize our, systems. For this reason, hydrogen plays a very important roles in today's and the future role of energy economy and all the countries, future. About the global emissions and hard to abate sectors, you can see two figures here. In the blue figures, that is energy use. It's energy consumption and CO2 emission, the red one. And as you can see nowadays, the mainly part of the CO2 emissions in the world is related to iron and steel. It's a very significant amount, not only in energy, but also in CO2 emissions. And, it's a little hard to abate, decreasing this amount of energy and CO2 emissions is a little difficult. We cannot easily, remove them, decrease their effects. And in this way, we need a critical and very important parameters to solve this problem. Hydrogen can play a very important role in this solving this problem. Secondly, chemicals, including the ammonia, can in the not second place, the third place, because this figure is from the attached reference. In my style, I can go in the trend, decreasing or increasing, but this is not in trend. But that I wanted to, reflect the opinion of the author. Yeah, and the chemicals, the second energy using and CO2 emission in the world. And certainly heavy-duty trucks that including the ships also, and not only the trucks that we can see in the roads. So these three, sector has the most energy demands and also CO2 emission of the world. And if we want to focus on decreasing the demand of energy or optimizing it, and also decreasing the emissions, these will be the main candidate to consider. Hydrogen is an element that has specific, characters. For example, as I mentioned in my previous, slide, no CO2 at the point of use. Instead of CO2, we have H2O, water, and it's completely at the way of decarbonization. Secondly, acts as fuel, feedstock, and energy storage. This element can play three roles at the with we can target three aims only with one shot in the other word, and we can use it as a fuel. We can use it for the energy storage and feedstock in our chemical processes. It's the very unique properties of this fuel, and powers industrial decarbonization, as I mentioned. In the future, it's play a important role in the decarbonization of the industrial and totally in the economic of the, the future world. About the type of the hydrogen, there are three type of the hydrogen: brown or gray, mostly gray, blue, and green. In some other categories, probably you see 4, 5, until 9 categories. You can see sometimes yellow hydrogen or pink hydrogen. These are in some references you can find them, but the main, category of the hydrogen is only these three of them. The gray hydrogen means that, normally we use natural gas or coal for producing hydrogen. In this process, a lot of CO2 release, and this is not a clean, process for us. Because of that, we say that gray. It's because it's not clean enough. So, for solving this problem, in the last decade, the scientists, researchers all over the world focused on, the process for carbon captures in the utilization and storage of this released CO2. This solution is for the after process. After process, we try to, start the carbon capture process. And with using this process, we can decrease the amount of CO2 released from 50 to 90, even in the very, the latest methods and latest studies, it decreased on until 90% how they can remove this carbon. This is a very good amount, but still this is a temporary solution, not a solution for the, for permanent. So what is the solution of, a permanent solution of the hydrogen? Because, okay, we realize that hydrogen is a very useful, very, playing a very important role in the future. So, but for obtaining this amount of hydrogen, we need to, make some process. This process causes some pollution. We need to solve this pollution, and after that, this hydrogen will play a very efficient role. So we reach the green hydrogen. Green hydrogen. In the green hydrogen, it's produced from electrolysis of water using the renewable energy resources. So renewable energy resources producing electricity power, and using this power, the electrolyzer produce H2O. It's the best way. It's the clean and safe way to produce the H2 or hydrogen. And So in the future, we need to be sure that the green hydrogen will be the the unique element, unique fuel that can play in this important role in the future of the economy. But this green hydrogen has some problem. It's very expensive, very expensive. Let's see that how expensive is it? Well, this slide also is the rest of the previous one. You can see that the difference between green, blue, and gray hydrogen, and the difference way. Blue and gray almost the same. Just the carbon capture, cause some cleanliness, decrease the pollution. Using, yes, let me say the SMR, steam methane reforming, this is the process. This process involves reacting natural gas, methane, CH4 also, all of them the same, with steam to produce hydrogen and carbon monoxide. It's working between 700 and 1000 degrees Celsius, presence of an appropriate metal catalyst according to following chemical reaction. You can see the reaction, and the CO2 is obvious over there. The SMR process is the traditional process, and the carbon capture is adapted to this process to reduce. But let's focus more on green hydrogen. Before that, let's see that what is the position of every hydrogen, every type of hydrogen in the nowadays world. Let's see that from the financial point of view, economic point of view. Let's see that what are their position. The problem is that clean green hydrogen has always been far more expensive than its dirty gray counterpart. This, if you see this figure, it's from Bloomberg, publication. Today, country by country, you can see the price of every kilogram of hydrogen production in the survey for the gray hydrogen, for the blue hydrogen, and for the green hydrogen that we discussed. And in the today was in almost all over the countries, green hydrogen is very expensive, super expensive than traditional gray, hydrogen, and even the blue hydrogen. But it's today's, story. In the coming years, especially in 2030 and even until 2050, this game will be changed. This story will be changed, and it's changing because of the, decarbonization policy of the countries, the sustainability requirement of the societies, and the fossil fuel restrictions and limitations. The country is forced to move to this, sector for the green hydrogen. And you can see also the India's, condition at the middle almost between Italy and Germany. We have two types of, gray hydrogen. That's one of them is existing plant. Existing plant sometimes use some subsidy from the government, and new plants, no, it's not any support from the governments, and because of that, there are a little difference in the prices out there. Two kinds of the gray hydrogen, and above the also blue and the green one. Especially and between gray and green and blue and green, there are a lot of a huge of different. Even at the maximum condition in country like Indonesia, for example, every kilogram of hydrogen, green hydrogen, obtain 12 USD dollars. It's a very expensive, very expensive. In this slide, you can see the average production cost of every type of hydrogen. For example, the gray is, averagely means that all over the world, totally, almost less and more, 2.13, but in some countries you can find even less than 1 USD dollars. Or for the blue one, the average is 3.1, and even in some countries you can find 1.8 USD dollars per kilogram. But above the green hydrogen, between the domain between 4.5 USD dollars to 12 USD dollars per kilogram, and averagely all over the world it's 6.4 kilogram. This difference, this gap between the prices of the production caused that for now, most of the hydrogen produced by the gray type. But it will be changed. It will be changed. Not very, far future. It's so close, so close. Yes. Let's see and forecasting that it's still from Bloomberg. Green hydrogen is cheaper than gray in 5 markets in 2030. In 2030 means that 5 years later, anyway, this report was belonging to 2023. Let's consider 2023 and 7 years later. And in 2023, in 5 countries in the world, including India, including Brazil, China, India, Spain, and Sweden, green hydrogen from new plants is going to start undercutting gray hydrogen. Very interesting, very interesting. From existing plants by the end of the decade. Wow, it's, it's a revolution, in my opinion, in the hydrogen production. Remarkably, this holds true even for green hydrogen plant built without subsidies. This is without subsidy. It's not for, pumping money from the government. No, it's because of, anyway, the policy of the, countries support this, method, but not just only pumping money. No. It is. And anyway, the restriction regarding the environmental rules and also the progress of the science, every day we have new methods, optimized, solutions. And according to the predictions, in 2030, 5 countries in the world have, better prices for the green hydrogen, even better than gray hydrogen. This is a revolution, as I mentioned, in the hydrogen production. Okay, so for the green hydrogen, I want to focus a little more in green hydrogen because the direction of my studies also focus on this area. I want to, clarify and expand the topic more, focusing on green hydrogen production. Yes, we mentioned that for the green hydrogen production, we are using the renewable energy resources for producing powered electricity that electrolyzer um, produce hydrogen using the water, you know. And this is the very simplest, definition of the process. And well, about the renewable energy sources, as you know, wind, solar, hydro power, geothermal, biomass, ocean, and these are the most important one. Anyway, there are some little groups also, but the most important one today is wind, solar, and geothermal. And today I want to talk about these three resources of the renewable energies. And yes, firstly, I want to talk about the solar energy. Solar energy can produce green hydrogen using two different ways. The first one is the PV panels. PV is the abbreviation of photovoltaic, solar photovoltaic driven hydrogen generation. PV panels produce electricity directly. This, electricity uh, you're running electrolyzer. Anyway, we have three type of electrolyzer. Also, for my case, most of the time I'm using PEM electrolyzer, but for the better understanding and clear presentation, I mentioned three type of electrolyzer also. Generally utilize solar energy to perform water electrolysis, splitting water H2O into hydrogen and oxygen gases. Schematically, you can see the process of that, in a very simple way. So this using the solar energy, we can firstly, with the PV panels, we can reach the hydrogen energy, and secondly, using the solar thermal collectors. In the solar thermal collectors, these, collector heating working fluid. It's this working fluid is most of the time is the oil. For example, terminal BP one. It's one of the common, and this boiling or heating oil running second cycle. For example, it can be a Rankine cycle. It's so common, organic Rankine ORC cycles. And this ORC cycle producing electricity, and this electricity again running electrolyzer and producing H2O. Okay, so for the solar one, we have two ways, photovoltaic or collector, and both of them has some benefit and limitations, but totally, um, the solar green hydrogen driven systems has limitation. The main limitation is obvious. It's obvious that, anyway, we have day and night. And according to this figure, you can see in winter, it's, for a normal country, not especially in, like Finland or some, quarter, equator country. Probably in India also some cities, following this trend also, as a normal one, not a, all over the world. The city is different point by point. In the winter, we have totally have 10 hours of, sunlight, and in the, summer, we have maximum 14 hours. What about the rest of 10 to 14 hours that we do not have any access to sunlight? So solar generation is variable. Solar energy is not a, constant. 24 hours energy, and it depends on the or not the weather. Kind of, for example, sometimes 1 week we have a cloudy weather. What else? What else? What should we do? What should we do in this occasion? Our industry cannot wait and suffer these damage. The other one, large solar farms require significant land area. Yes, yes, yes. And mm, the farms, solar panel farms need a lot of spaces, and their maintenance also a little complicated. It's affected by soil, affected by the angles of the sun. It's very sensitive. And as I mentioned in the third section, many industries need continuous high purity hydrogen, continuous and high purity. These variation of the sun irradiation, also solar power, is a completely a big problem and risk for these systems that reject this idea using only solar energy for uh, high green hydrogen production. Let's see what about the wind energy. Let's see what about the wind energy. And as I mentioned, electricity generation from wind energy illustrated minimum negative impact on the environment compared to other energy resources. Because, anyway, every renewable energy source has some negative impact, in the environment, in the ecosystem, even the, wind turbines has negatively because they have some sound pollution, they damage some birds. But anyway, this is the minimum amount of, negative effects. And comparison of the rest of the, renewable energy resources, wind energy is the best one. Anyway, all the renewable energy resources are good. We are talking in the better or best, not something that moderate or worse. Better or best. Let's talk in this standard, not something that of fossil fuel power plants. That we completely we are in the other level of speech. And wind offers higher and steadier output than solar, improving economics. According to the solar system, the wind-powered hydrogen, has more stable, more steady, and more reliable. More reliable is a better option for producing, green hydrogen. Even already in North Sea, North America, China, and Australia, millions of tons of hydrogen are producing per year using the offshore wind farms. Offshore wind farms between the ocean, a lot of turbines, and producing a huge amount of electricity. This electricity produce millions tons of hydrogen per year. Is the wind energy the final solution or not? Let's see. Let's see. In this section, I want to talk about one of my own research. When I was in the, no, I stayed in my second PhD in north of Mexico, close to the border of United States and Mexico. There was a state named Chihuahua. The name of the capital of that state was Ciudad Juarez. It's a border city. The north section was El Paso, Texas. That was south of the, even in the maps you can see. The south of Texas was El Paso City and Ciudad Juarez. We were neighbor together. Even my apartment over there in Civil Juarez was so close to the United States. I can read the plug number of the cars. We were so close. Ciudad Juarez, one of the most industrial city in the world, one of the most of them. And according to some statistics over there, I hear that 700, famous company has some, facilities, some sections over there from all over the world, from the North America, Europe, Japan, of course, from India, China. A lot of companies were over there, and a huge amount of energy demand, and a lot of pollution was over there required. We wanted to study that is the wind energy is suitable to cover the energy demand and reduce the pollution of these cities, companies or not. The company's name in Spanish is Maquiladoras. Maquiladoras is so famous over there. And we studied this, topic, and it's published in a Colombian journal. And we wanted to see that is there any potential or, economic accessibility of the wind power plant in this city or not. And we used 5 types of wind turbine over there. And for our simulation, anyway, we used the software Red Screen. Red Screen is a Canadian software and open source. You can easily download and use it without any, concerning about the license or something like this. It's a very, very good and useful, software for power plants, feasibility analysis, calculations, and modeling. We realized that in not only large scales, but also medium and small scale wind turbines is not working over there economically, economically feasible, because we realized that for the economic condition of the Mexico, we need at least 6 meters per second wind speed. But if you see that figure, the blue bars are the average wind speed in that city, and most of the months of the year, the speed was even less than 5 meter per second, and economically it was not feasible. So there was potential demand for the wind power plants, but unfortunately, from the economical point of view, it's rejected. It's rejected, and there is not any justification for installation of the wind turbine over there. So producing the green hydrogen over there using the wind turbine is declined, and it was not possible, unfortunately, or probably fortunately. Anyway, so I wanted to declare that wind energy is only suitable for special point of the world's special point of the countries, not all over the countries. And even in this point, it depends on the wind speed. Anyway, it's not like solar energy that we have regularly day, night. No. It's more steady state, more steadier than solar wind energy. But even these kind of problems, direct dependence on the wind speed cause some unreliability, and this reliability is risk for green hydrogen production for serious demand of hydrogen. So let's see the third candidate. Anyway, this is my favorite candidate, and geothermal energy is my personally favorite, source of renewable energy. I really enjoy working with geothermal energy resources, and most of my research direction also is focused on geothermal energy, and I prefer them to the rest of. I have reason. I have reason. It's not only some personal interest. Okay, geothermal energy uses heat from within the earth to generate electricity to provide direct heat. It is renewable, it continuously flow from Earth's interior, and this cycle is, renewable. Every moment is renewable. Every moment is renewable, reliable. In the previous two energy resources, I thought that, okay, the solar energy depends on the weather condition, day, night. Wind turbine depends on, rely on the windy speed, and some days we do not have windy speed, and it's completely out of the network. But above the geothermal energy, no, it's continuously working 24 hours, 7 days, all over the in days of a year, and it's so reliable source of energy, low emission, often understand outside volcanic regions, tough modern drilling span. And there are some other benefit of geothermal energy. For example, from the point of as I mentioned, that wind turbines has some sound pollution, but geothermal energy do not have this, and it's almost focused on some area. It's not expanding that solar panel farms very vast areas. So geothermal energy is a reliable, more reliable source of energy, and it's a completely excellent match for green hydrogen. Why? Why? As I mentioned, it has a constant power, and electrolyzers run more efficiently when energy is stable. I mentioned a couple of times in some serious and high demand, sectors of industry like steel, like ammonia, even refinery. We have a constant and huge amount of sources. Solar and wind sometimes this variation cause uncertainty, but this is a constant one. This is the benefit of the geothermal energy. Lower cost. Geothermal power often produce cheaper than the rest of the resources. Anyway, the initial investment of the geothermal energy is high. Initial investment is high, but after that, the price per unit is cheaper and lower. Water availability in some areas, not all of them, some areas, some geothermal systems bring up water, and we can even use that in our, electrolyzer. So the demand for water is also satisfied using this, area, and very small footprint and negative effect. Anyway, wind energy a little better than geothermal, but even geothermal is a good condition also. So I want to mention to one of my own papers again. Geothermal energy has also some limitations. The main limitation of the geothermal energy is the very low efficiency. At the basic single flash geothermal cycle, the efficiency between 10 to 14%. Sometimes it's even less, 8%, 9%. Is very low percent of efficiency. And firstly, we need to solve this problem. We need to increase this problem. After that, let's focus on green energy. In this work, I use the two-stage ORC for recover the waste heat from the single flash geothermal cycle, and also I use the cold exergy of a LNG that want to transfer to city, and this system using this system I increase efficiency significantly. So for the geothermal energy, firstly, we need to increase the efficiency, and reach to a desired point, desired amount. After that, we can think about the integration of the system to electrolyzer. The other, in my other publication, it's publishing desalination. Okay, I used the double flash geothermal, and I recovered the transcritical O2 cycle. I used only a part of the produced power to running a RO, reverse osmosis. That was, in the initial try to see that, okay, what about the RO system? The result was good. And here you can see that in this figure, and also in the table, with using only a little, sacrificing only a little amount of our exergy efficiency for producing the RO. In this case, I studied RO, but anyway, you can replace it easily with PEM electrolyzer. With sacrificing a little amount of our exergy efficiency, not energy, exergy, second thermodynamic laws, we can reach a reasonable amount of, in this case, fresh water, and in the second case, we can reach the green hydrogen. And from the logic and science point of view, this is the feasibility of these systems. So for the future work for this area, currently I'm working in this system, and in this system, I designed the polygeneration system for producing hydrogen. How does it work? In this case, we have a basic geothermal system that it's waste heat recovered by ORC and VCC cycle. We are producing electricity, cooling, heating, and also hydrogen at the same time. It's a polygeneration system. And for the better performance, for the increasing our parameters, design parameters, including the net power output, including energy efficiency, including exergy efficiency, I use solar panel. You can see at the top of the cycle. What is it? The reason of using the solar energy in the system is that before entering the saturated vapor to our steam turbine, I make it superheat. Superheat steam or superheat vapor has a better performance in running our steam turbine and cause a huge amount of power, and this power cause a better performance, desired performance of our system. As you can see, not only all amount of our productive power, only a part of it use it for the our electrolyzer section, I use the PEM electrolyzer to produce hydrogen and oxygen at the same time, completely a green hydrogen using a polygeneration combined system. We combine anyway. Our main system is geothermal, and we combine it with solar system. At the same time, we recovered the waste heat of basic geothermal system to increase our efficiencies. We are producing more power and using only a part of this power for producing hydrogen. This system for the future world is a desired system, and it's completely promising way that we design not only from energy, exergy, and environmental point of view, but also from economical point of view, a desired system that cover all the necessity of all the demands of our cities, our industries, and our the rest of the sections that we are dealing with in our systems. Anyway, there are more aspects of this design system, and even this system is expanded from other aspects. But just I wanted to mention some of our future work. Anyway, this is not completely future because we almost finished this research. I want just to review it, but it's not published yet. And about the conclusion of my presentation, as I mentioned, hydrogen is essential for decarbonizing hard-to-abate sectors such as steel, ammonia, and refining. As I mentioned in the previous initial slides, dealing with three sectors is a little tough. They need a lot of energy, and they are producing a lot of CO2. And also, it's a little sensitive. If we want to, replace them, their, fuel with a new fuel, we need a new installment, and this installment will need a lot of, cost and investment. But using hydrogen can easily use the natural gas piping system easily. You do not need any new piping system. This is another benefit of hydrogen. Also, green hydrogen remains costlier than gray hydrogen, but prices are expected to fall significantly. For now, yes, the gray hydrogen is very cheap, but in the coming years, probably in the coming 5 years, India will be one of the countries that we will have at the pessimistic point of view. We will have at the same price the green hydrogen and gray hydrogen at the same price. Solar, wind, and especially geothermal energy provide viable pathway for large-scale green hydrogen production. We talked about them less and more widely. I tried to, clarify, start with the benefits and the disadvantage of every, resources to you. And geothermal powered electrolyzers offer stable, efficient, and low emission hydrogen generation. As I mentioned until now, and according to my studies, I offered that hydrogen, geothermal power, green hydrogen production is the most desired one. Even, with the combined system and polygeneration system, we can reach the better result, better output. And also, expanding renewable-based hydrogen can accelerate the transition toward a sustainable, carbon-free industrial future. And about my biography, anyway, my name is Yashar Aryan, sir, and I obtained 2 PhD. The first one from China in Hoha University in engineering mechanics, and my second PhD was in advanced engineering sciences from Mexico. I was the government scholarship of the Mexican government, and I was over there for 3.5 years, and currently I'm working in NCKU in Taiwan. Also, in the last June, I selected as the best young researcher in Budapest conference, JTAC conference, and I won a travel grant to this conference over there. Anyway, thank you for your attention. I hope that was a useful presentation. If you have any question, I will be available to respond to your question. Thank you so much.
Thank you, sir. Dear participants, if you have any queries, kindly proceed. Sir, some of the participants posted in chat box some questions, sir.
Yes, yes. Let me check. Okay. Okay, the first one. Okay, let me. Is there any possibility for the hydrogen onboard production by electrolyzer? Yes, there is this possibility. As I mentioned, actually, I wanted to include the electrolyzer types also in this presentation, but because of the lack of time and, if I want to speak also the different type of the electrolyzer, it will take a lot of time, and probably I could not, focus all the topics. Anyway, I understand that I mostly watch to the topic from the mechanical engineering point of view, especially renewable energies. Probably as a chemical engineer is a different point of view. But anyway, my view was focused on mostly on green hydrogen. But totally your response is yes. And the other one, how can ammonia mediate it, hydrogen storage and transportation enable the widespread adoption of low carbon steel production? The transportation is the main even in the geothermal systems. I mentioned that we have sometimes a serious problem regarding the transportation because the field and our station's location is very far from the cities or the places, and we need some, special and very serious facilities for the transportation, and it can be studied. That okay, this transportation also will affect our study and location or not. Well, let me give you an example. For example, in United States, there are two sections. In the one section, they are using the electric vehicles, and the other section hydrogen, because according to the policy of every state, their aims is different. Their aims is different, and sometimes they are using electric vehicles, and sometimes they are using hydrogen using vehicles. And they say that okay, hydrogen using vehicles have some advantages. For example, they are using a low speed, they are faster than electric vehicles. So it's not a constant response, and it depends case by case. The other one, thank you for the session. My pleasure, Mr. Thomas Selvan, and session 8. Much thank you. Very nice and good explanation. My pleasure. It was my honor to have this session with you. Thank you, Professor. And if you have other questions, I will be available.
Thank you, sir. Once again, thank you for your spending a valuable time for us. Thank you,
My
sir.
pleasure. I'm so happy. And I hope to see you again. And special thanks from Professor Karthik to invite me to this session also. Thank you.
Thank you, sir. HOD sir, finally we concluded the session.
Yes, sir. Sir, very much thankful to you, sir.
Sorry?
Sir, very much thankful to you, sir. Thank you.
Oh, okay. My pleasure. It's my pleasure.
Thank you, sir. Thank you very much.
In final session, concluded with a vote of thanks. Thank you, Dr. Yashar Aranvar, sir, for your incredibly insightful presentation on hydrogen for industrial carbonization. You have expertly guided us through your technical pathways and strategic imperatives for transforming the hard-to-abate sectors of this steel and ammonia and refining. Your analysis provided a clear and crucial roadmap highlighting not only the potential of hydrogen, but also the economic and the systematic realities of the essential transition. The session has been both enlightening and essential for anyone engaged in the future of clean industry. Once again, a very warm thank you, sir, Dr. Yashar Aranvar, sir, for your valuable time and for sharing your valuable feedback with us. Thank you, sir.
My pleasure, and I hope that I could present, a benefit presentation to you. It was my pleasure. It's my honor to staying with you, and I hope that in the future I will have the opportunity to be your guest. Thank you.
Okay, sir.
Thank you so much, sir.
Okay, sir. Thank you.
Bye.
Dear participant, we concluded today's session. We sincerely appreciate your attendance and engagement. Our program will resume tomorrow at 6 p.m. Thank you all. Thank you for your support and cooperation. Thank you, sir. Kindly find a feedback link in session 8 in chat box. Thank you.